Okay, we are going to try this example. It's not really an example because you're going to try it, but here are 3 problems for you to try. Go ahead and graph A, B, and C, each on their own coordinate plane, and then press pause. First press pause, graph them, and then come on back and check your answers. So we're going to try and identify a model that's appropriate for each set by graphing. So for the first one that I have in purple there, I graphed the 4 points, and I got those 4 points. So those 4 points appear to be linear. So I'm going to call this one a linear model. So a linear model would be best for this one right here. The next one we have in pink, this graph right here. So when I plot these points, because it looks like, you know, when I come over here, it looks like this is going to bounce back up. Because it looks like it's going to bounce back up, I'm going to call this one a quadratic. It's got to have that bounce back up to graphically represent that quadratic model. And then our last one, that last one in that pretty blue right there, I plotted the points. Let's try and get rid of that. There we go. Plotted those blue points. And this one, it almost looked like it was linear, except it's got that little bit of a curve to it. So I'm going to assume that that little bit of a curve is going to be a nice exponential model. So an exponential model. Now remember what these models are. So the linear model is y equals mx plus b. The quadratic model is y equals ax squared plus bx plus c. And the exponential model is y equals a times b raised to the x power. Okay, now we're going to look at our table of values and see if we can't come up with what's happening here. What kind of function is represented? Well, here on the left we have an arithmetic sequence, and on the right we have a geometric sequence, and I'm going to show you both of those. So the one on the left, let's look at our change in x. So our change in x is going to go up by 1, up by 1, up by 1, and up by 1. This is very convenient. Our change in y increases by 4, increases by 4, increases by 4, increases by 4. So if you recall, the common difference here would be 4. This has a constant rate of change, so I'm going to call this right here. This is your first difference. The first difference, apologize for my handwriting. The first difference is constant. Therefore, we have a linear model. This is a linear model. Now in a geometric sequence, look at what happens. Our change in x is going to go up by 1, up by 1, up by 1, up by 1. Our change in y, that doesn't go up by a certain amount. It looks like it's got a common multiplier, a common ratio. So we know we multiply by 3, multiply by 3, multiply by 3, multiply by 3. So this is a common ratio. So our change in x is constant, but our change in y is a common ratio. That's what makes it a geometric sequence, right? And that's going to give us an exponential function. So remember when we had those exponential functions, y equals the initial value times b to the x. So in this case, our initial value is when x is 0. So our initial value is 1. Our b value is our common ratio. So this would be y equals 3 to the x. Y equals 3 to the x. Pretty cool. So cool, I'm going to come back over here to the linear model. Y equals, our slope is 4, and our y-intercept is 6. See, so from these two tables, we can actually get our model as an equation. Now, what happens, though? What happens with the quadratic model? So you'll know it's a quadratic model when our change in x, plus 1, plus 1, plus 1, plus 1, plus 1. Our change in y, let's see what's happening there. Divide by 8 or multiply by 1/8. No, not multiplied by 1/8. So we're not multiplying by the same amount because 4 times 5 is 20, right? -2 times -2 is 4, so that's not the same number at all. So let's go with our difference. So this would be subtract 14. Subtract 4. Add 6. This is weird. Add 16. Add 26. Well, those look nice. Look, that looks real. Look, they all end in 6. Okay, maybe, look, I add 10. Let's see if that's something. So this is our second difference. So our second difference for y. So our second difference for y. Add 10. Yep, -14 plus 10 is -4. Add 10, -4 plus 10 is 6. Yeah, 6 plus 10 is 16. 16 plus 10 is 26. That second difference is common. So we have a common second difference. A common second difference. Therefore, we have a quadratic model. Now this quadratic model would be a bit difficult for me to come up with the parameters of A, B, and C. It's not as easy as the exponential and the linear, so I'm going to leave it right there. But that's how, with a table of values, we can find and determine, or even a set of ordered pairs, whether or not we have a linear, exponential, or quadratic model. So in this example, we're going to determine which kind of function best models the data at the left, and then when we write the equation, that's when we're going to use our calculators. So make sure that you have your calculator handy, because in this next example, we're going to be using it.